Hi everyone, and welcome to Lecture 9 for CS230. Today we're going to discuss an advanced topic that will be kind of the marriage between deep learning and another field of AI, which is reinforcement learning. And we will see a practical application and how deep learning methods can be plugged in another family of algorithms. So it's interesting because deep learning methods and deep neural networks have been shown to be very good function approximators. Essentially, that's what they are. We're giving them data so that they can approximate a function. There are a lot of different fields which require these function approximators. And deep learning methods can be plugged in all these methods. This is one of these examples. So we'll first motivate the setting of reinforcement learning. Why do we need reinforcement learning? Why can't we use deep learning methods to solve everything? There are some set of methods that we cannot solve with deep learning. And reinforcement learning applications are examples of that. We will see an example to introduce an algorithm of a reinforcement learning algorithm called Q-learning. And we will add deep learning to this algorithm and make it deep Q-learning. As we've seen with generative adversarial networks and also deep neural networks, most models are hard to train. We had to come up with Xavier initialization, with dropout, with batch norm, and myriads of methods to make these deep neural networks train. In GANs, we had to use methods as well in order to train GANs and tricks and hacks. So here we will see some of the tips and tricks to train deep Q-learning, which is a reinforcement learning algorithm. And at the end, we will have a guest speaker coming to talk about advanced topics, which are mostly research, which combine deep learning and reinforcement learning. Sounds good? Okay, let's go. So deep reinforcement learning is a very recent field, I would say, although both fields are reinforcement learning has existed for a long time. Only recently, it's been shown that using deep learning as a way to approximate the functions that play a big role in reinforcement learning algorithms has worked a lot. So one example is AlphaGo, and you probably all have heard of it. It's Google DeepMind's AlphaGo has beaten world champions in a game called the game of Go, which is a very old strategy, old game. And the one on the right here, or on your right, human level control through deep reinforcement learning, is also a Google DeepMind paper that came out and hit the headlines on the front page of Nature, which is one of the leading multidisciplinary peer-reviewed journals in the world. And they've shown that with deep learning plugged in a reinforcement learning setting, they can train an agent that beats human level in a variety of games. And in fact, these are Atari games. So they've shown actually that their algorithm, the same algorithm reproduced for a large number of games, can beat humans on all of these games. Most of these games, not all of these games. So these are two examples. Although they use different sub-techniques of reinforcement learning, they both include some deep learning aspect in it. And today we will mostly talk about the human level control through deep reinforcement learning, also called deep Q network, presented in this paper. So let's start with motivating reinforcement learning using the AlphaGo setting. This is a board of Go, and the picture comes from DeepMind's blog. So Go, you can think of it as a strategy game where you have a grid that is up to 19 by 19, and you have two players. One player has white stones and one player has black stones. And at every step in the game, you can position a stone on the board, on one of the grid cross. The goal is to surround your opponent, so to maximize your territory by surrounding your opponent. And it's a very complex game for different reasons. One reason is that you have to be, you cannot be short-sighted in this game. You have to have a long-term strategy. Another reason is that the board is so big. It's much bigger than a chessboard, right? Chessboard is 8 by 8. So let me ask you a question. If you had to solve or build an agent that solves this game and beats humans, or plays very well at least, with deep learning methods that you've seen so far, how would you do that? Someone wants to try? So let's say you have to collect a data set, because in classic supervised learning, we need a data set with X and Y. What do you think would be your X and Y? Yeah?
The game board is the input, and then the output is the probability of victory from that position.
Okay, input is game board, and output is probability of victory in that position. So that's a good one, I think, input, output. What's the issue with that one? So, yeah.
It's hard to represent what the probability of winning is.
Yeah, it's super hard to represent what the probability of winning is from this board. Even, like, nobody can tell. Like, even if I ask an expert human to come and tell us what's the probability of black winning in this or white winning in this setting, they wouldn't be able to tell me. So this is a little more complicated. Any other ideas of data sets? Yeah.
The grid and then the next action.
Okay, good point. So we could have the grid, like this one, and then this is the input, and the output would be the move, the next action taken by probably a professional player. So we would just watch professional players playing, and we would record their moves, and we would build a data set of what is a professional move. And we hope that our network, using this input-output, will at some point learn how the professional players play, and given an input, a state of the board, we'll be able to decide of the next move. What's the issue with that? Yep.
You need a whole lot of data in terms of becoming a whole lot of versions of that.
Yeah, you need a whole lot of data. Why? And you said it. You said because we need basically to represent all types of positions of the board, all states. So if we were actually, let's do that. If we were to compute the number of possible states of this board, what would it be? It's a 19 by 19 board. Remember what we did with adversarial examples. We did it for pixels, right? Now we're doing it for a board. So what's the question first is, yeah, you want to try?
3 to the 19 squares.
Yeah. 3 to the power 19 times 19, or 19 squared. Yeah, so why is it that? Why is it this?
Each spot can have a seed, have no stone, a white stone or a black stone.
Yeah. Each spot, and there are 19 times 19 spots, can have 3 states, basically, no stone, white stone, or black stone. So this is the all possible state. This is about 10 to the 170. So it's super, super big. So we can probably not get even close to that by observing professional players. First, because we don't have enough professional players, and because we're humans and we don't have infinite lives, so the professional players cannot play forever. They might get tired as well. So one issue is the state space is too big. Another one is that the ground truth probably would be wrong. It's not because you're a professional player that you will play the best move every time, right? Every player has their own strategy. So the ground truth we're having here is not necessarily true, and our network might not be able to beat these human players. What we're looking into here is an algorithm that beats humans. Okay? Second one, too many states in the game, as you mentioned. And third one, we will likely not generalize. The reason we will not generalize is because in classic supervised learning, we're looking for patterns. If I ask you to build an algorithm to detect cats versus dogs, it will look for what the pattern of a cat is versus what the pattern of a dog is, and the convolutional filters will learn that. In this case, it's about a strategy. It's not about a pattern. So you have to understand the process of winning this game in order to make the next move. You cannot generalize if you don't understand this process of long-term strategy. So we have to incorporate that. And that's where RL comes into place. RL is reinforcement learning, a method that could be described with one sentence as automatically learning to make good sequences of decision. So it's about the long term. It's not about the short term. And we would use it generally when we have delayed labels, like in this game. The label that you mentioned at the beginning was probability of victory. This is a long-term label. We cannot get this label now, but over time, the closer we get to the end, the better we are at seeing the victory or not. And it's to make sequences of decisions. So we make a move, then the opponent makes a move, then we make another move. And all the decisions of these moves are correlated with each other. Like you have to plan in advance. When you're human, you do that. When you play chess, when you play Go. So examples of RL applications can be robotics. And it's still a research topic, how deep RL can change robotics. But think about having a robot walking from here, and you want to send it there. You want to send the robot there. What you're teaching the robot is, if you get there, it's good, right? It's good, you achieved the task. But I cannot give you the probability of getting there at every point. I can help you out by giving you a reward when you arrive there and let you trial and error. So the robot will try and randomly initialize, the robot will just fall down at first, get a negative reward. Then repeat. This time the robot knows that it shouldn't fall down, it shouldn't go down. It should probably go this way. So through trial and error and reward on the long term, the robot is supposed to learn this pattern. Another one is games, and that's the one we will see today. Games can be represented as a set of reward for a reinforcement learning algorithm. So this is where you win, this is where you lose. Let the algorithm play and figure out what winning means and what losing means until it learns. Okay? The problem with using deep learning is that the algorithm will not learn because this reward is too long term. So we're using reinforcement learning. And finally, advertisement. So a lot of advertisements are real-time bidding. So you want to know, given a budget, when you want to invest this budget. And this is a long-term strategy planning as well that reinforcement learning can help with. Okay, so this was the motivation of reinforcement learning. We're going to jump to a concrete example that is a super vanilla example to understand Q-learning. So let's start with this game or environment. So we call that an environment generally, and it has several states. In this case, 5 states. So we have these states, and we can define rewards, which are the following. So let's see what is our goal in this game. We define it as maximize the return or the reward on the long term. And what is the reward is the numbers that you have here that were defined by a human. So this is where the human defines the reward. Now what's the game? The game has 5 states. State 1 is a trash can and has a reward of +2. State 2 is a starting state, initial state. And we assume that we would start in the initial state with a plastic bottle in our hand. The goal would be to throw this plastic bottle in a can. If it's the trash can, we get +2. If we get to state 5, we get to the recycle bin, and we can get +10. Super important application. State 4 has a chocolate. So what happens is if you go to state 4, you get a reward of 1 because you can eat the chocolate, and you can also throw the chocolate in the recycle bin, hopefully. Does the setting make sense? So these states are of 3 types. One is the starting state, initial, which is brown. The normal state, which is not a starting, neither a starting nor an ending state, and it's gray. And the blue states are terminal states. So if we get to the terminal state, we end up a game or an episode, let's say. Does the setting make sense? Okay, and here are 2 possible actions. You have to move. Either you go on the left or you go on the right. An additional rule we'll add is that the garbage collector will come in 3 minutes, and every step takes you 1 minute. So you cannot spend more than 3 minutes in this game. In other words, you cannot stay at the chocolate and eat chocolate forever. You have to move at some point. Okay? So one question I'd have is, how do you define the long-term return? Because we said we want a long-term return. We don't care about short-term returns. what do you think is a good way to define a long-term return here? Yeah.
Sum of the terminal states.
The sum of the terminal states.
No, the sum of how many points you have when you reach a terminal state.
The sum of how many points you have when you reach a terminal state. So let's say I'm in state 2. I have 0 reward right now. If I reach the terminal state on the on your left, the +2, I get +2 reward, and I finish the game. If I go on the right instead, and I reach the +10, you're saying that the long-term return can be all the sum of the rewards I got to get there, so +11. So this is one way to define the long-term return. Any other ideas?
You also want to incorporate the time step, probably take out, reduce the cost or the reward.
Yeah, we probably want to incorporate the time steps and reduce the reward as time passes. And in fact, this will be called a discounted return versus what you said would be called a return. Here we will use a discounted return, and it has several advantages. Some are mathematical, because the return you described, which is not discounted, might not converge. It might go up to +infinity. This discounted return will converge with an appropriate discount. So intuitively also, why is the discounted return intuitive? It's because time is always an important factor in our decision making. People prefer cash now than cash in 10 years, right? Or similarly, you can consider that the robot has a limited life expectancy, like it has a battery and loses battery every time it moves. So you want to take into account this discount of, if I can eat chocolate close, I go for it because I know that if the chocolate is too far, I might not get there because I'm losing some battery, some energy, for example. So this is the discounted return. Now, if we take gamma equals 1, which means we have no discount, the best strategy to follow in this setting seems to be to go to the left, to go to the right, starting in the initial state 2. Right. And the reason is it's a simple computation. On one side I get +2, on the other side I get +11. What if my discount was 0.1? Which one would be better? Yeah, the left would be better, directly to +2. And the reason is because we compute in our mind, we just do 0 plus 0.1 times 1, which gives us 0.1, plus 0.1 squared times 10. And it's less than 2. We know it. Okay? So now we're going to assume that the discount is 0.9. And it's a very common discount to use in reinforcement learning. And we use a discounted return. So the general question here, and it's the core of reinforcement learning in this case of Q-learning, is what do we want to learn? And this is really, think of it as a human. What would you like to learn? What are the numbers you need to have in order to be able to make decisions really quickly, assuming you had a lot more states than that and actions? Any ideas of what we want to learn? What would help our decision making?
Optimal action at each state.
Optimal action at each state. Yeah. That's exactly what we want to learn. For given a state, tell me the action that I can take. And for that, I need to have a score for all the actions in every state. In order to store these scores, we need a matrix, right? So this is our matrix. We will call it a Q table. It's going to be of shape number of states times number of actions. If I have this matrix of scores and the scores are correct, I'm in state 3. I can look on the third row of this matrix and look what's the maximum value I have. Is it the first one or the second one? If it's the first one, I go to the left. If it's the second one that is maximum, I go to the right. This is what we would like to have. Does that make sense, this Q table? So now, let's try to build a Q table for this example. If you had to build it, you would first think of it as a tree. Oh, and by the way, every entry of this Q table tells you how good it is to take this action in that state. State corresponding to the row, action corresponding to the column. So now how do we get there? we can build a tree, and that's similar to what we would do in our mind. We start in S2. In S2, we have two options. Either we go to S1, we get 2, or we go to S3 and we get 0. From S1, we cannot go anywhere, it's a terminal state. But from S3, we can go to S2 and get 0 by going back, or we can go to S4 and get 1. That makes sense? From S4, same. We can get 0 by going back to S3, or we can go to S5 and get plus 10. Now, here I just have my immediate reward for every state. What I would like to compute is the discounted return for all these states, because ultimately, what should lead my decision making in a state is, if I take this action, I get to a new state, what's the maximum reward I can get from there in the future? Not just the reward I get in that state. If I take the other action, I get to another state. What's the maximum reward I could get from that state? Not just the immediate reward that I get from going to that state. So what we would do, we can do it together. Let's say we want to compute the value of the actions from S3 going right and left. From S3, I can either go to S4 or S2. Going to S4, I know that the immediate reward was 1, and I know that from S4, I can get plus 10. This is the maximum I can get. So I can discount this 10, multiplied by 0.9. 10 times 0.9 gives us 9, plus 1, which was the immediate reward, gives us 9, gives us 10. So 10 is the score that we give to the action go right from state S3. Now, what if we do it from one step before, S2? From S2, I know that I can go to S3. And to S3, I get 0 reward. So the immediate reward is 0. But I know that from S3, I can get 10 reward, ultimately, on the long term. I need to discount this reward from one step. So I multiply this 10 by 0.9. And I get 0 plus 0.9 times 10, which gives me 9. So now, in state 2, going right will give us a long-term reward of 9. Make sense? And you do the same thing. You can copy back that going from S4 to S3 will give you 0 plus the maximum you can get from S3, which was 10, discounted by 0.9. Or you can do it from S2. From S2, I can go left and get plus 2, or I can go right and get 9, and the immediate reward would be 0, and I will discount the 9 by 0.9 and get 8.1. So that's the process we would do to compute that, and you see that it's an iterative algorithm. I will just copy back all these values in my matrix, and now if I'm in state 2, I can clearly say that the best action seems to say go to the left, because the long-term discounted reward is 9, while the long-term discounted reward for going to the right is 2. And I'm done. That's Q-learning. I solved the problem. I had a problem statement. I found a matrix that tells me in every state what action I should take. I'm done. So why do we need deep learning? It's a question we will try to answer. So the best strategy to follow with 0.9 is still right, right, right. And the way I see it is I just look at my matrix at every step, and I follow always the maximum of my row. So from state 2, 9 is the maximum, so I go right. From state 3, 10 is the maximum, so I still go right. And from state 4, 10 is the maximum, so I go right again. So I take the maximum over all the actions in a specific state. Okay? Now, one interesting thing to follow is that when you do this iterative algorithm, at some point it should converge. And ours converged to some values that represent the discounted rewards for every state and action. There is an equation that this Q function follows. And we know that the optimal Q function follows this equation. The one we have here follows this equation. This equation is called the Bellman equation. And it has two terms. One is R, and one is discount times the maximum of the Q scores over all the actions. So how does that make sense? Given that you're in a state S, you want to know the score of taking action A in this state. The score should be the reward that you get by going there, plus the discount times the maximum you can get in the future. That's actually what we used in the iteration. Does this Bellman equation make sense? Okay, so remember, this is going to be very important in Q-learning, this Bellman equation. It's the equation that is satisfied by the optimal Q table or Q function. And if you try out all these entries, you will see that it follows this equation. So when Q is not optimal, it's not following this equation yet. We would like Q to follow this equation. Another point of vocabulary in reinforcement learning is a policy. Policy is denoted P sometimes or mu, and pi. Pi of S is equal to argmax over the actions of the optimal Q that you have. What it means, it's exactly our decision process. It's given that we're in state S, we look at all the columns of this state S in our Q table, we take the maximum. And this is what pi of S is telling us. It's telling us this is the action you should take. So pi, our policy, is our decision making. Okay. It tells us what's the best strategy to follow in a given state. Any questions so far? Okay, and so I have a question for you. Why is deep learning helpful? Yes?
Number of states is not, it's way too large for Go.
Yeah, that's the reason. Number of states is way too large to store a table like that. So like if you have a small number of states and number of actions, then easy, you can use a Q table. You can, at every step, look into the Q table. It's super quick and find out what you should do. But ultimately, this Q table will get bigger and bigger depending on the application, right? And the number of states for Go is 10 to the power 170 approximately, which means that this matrix should have a number of rows equal to 10 with 170 zeros after. I mean, you know what I mean. It's very big. And number of actions is also going to be bigger. In Go, you can place your action everywhere on the board that is available, of course. Okay, so way too many states and actions. So we would need to come up with maybe a function approximator that can give us the action based on a state instead of having to store this matrix. That's where deep learning will come. So just to recap these first 30 minutes, in terms of vocabulary, we learn what an environment is. It's the general game definition. An agent is the thing we're trying to train, the decision maker. A state, an action, reward, total return, a discount factor, the Q table, which is the matrix of entries representing how good it is to take action A in state S. A policy, which is our decision-making function, telling us what's the best strategy to apply in a state. And Bellman equation, which is satisfied by the optimal Q table. So now we will tweak this Q table into a Q function. And that's where we shift from Q learning to deep Q learning. So find a Q function to replace the Q table. Okay, so this is the setting. We have our problem statement, we have our Q table, we want to change it into a function approximator that will be our neural network. Does that make sense how deep learning comes into reinforcement learning here? So now we take a state as input, forward propagated in the deep network, and get an output which is an action score for all the actions. It makes sense to have an output layer that is the size of the number of actions, because we don't want to give an action as input and a state as input and get the score for this action taken in this state. Instead, we can be much quicker. We can just give the state as input, get all the distribution of scores over the output, and we just select the maximum of this vector, which will tell us which action is best. So if we're in state 2, let's say, here. We're in state 2, and we forward propagate state 2, we get two values, which are the scores of going left and right from state 2. We can select the maximum of those, and it will give us our action. The question is how to train this network. We know how to train it. We've been learning it for 9 weeks. Compute the loss, backpropagate. Can you guys think of some issues that make this setting different from a classic supervised learning setting?
The reward changes dynamically. The reward changes dynamically.
The reward changes dynamically. So the reward doesn't change. The reward is set. You define it at the beginning. It doesn't change dynamically. But I think what you meant is that the Q scores change dynamically. That's true. The Q scores change dynamically. But that's probably OK, because our network changed. Our network is now the Q score. So when we update the parameters of the network, it updates the Q scores. What's another issue that we might have?
No labels.
No labels. Remember, in supervised learning, you need labels to train a network. What are the labels here? And don't say compute the Q table, use them as labels. It's not going to work. OK, so that's the main issue that makes this problem very different from classic supervised learning. So let's see how deep learning can be tweaked a little. And we want you to see these techniques because they're helpful when you read a variety of research papers. We have our network. Given a state gives us two scores that represent actions for going left and right from this state. The loss function that we'll define, is it a classification problem or a regression problem? Regression problem. Because the Q score doesn't have to be a probability between 0 and 1. It's just a score that you want to give. And that should mimic the long-term discounted reward. So in fact, the loss function we can use is the L2 loss function. Y minus the Q score squared. So let's say we do it for the Q going to the right. The question is, what is Y? What is the target for this Q? And remember, what I copied on the top of this slide is the Bellman equation. We know that the optimal Q should follow this equation. We know it. The problem is that this equation depends on its own Q. You know, like you have Q on both sides of the equation. It means if you set the label to be R plus gamma times max of Q stars, then when you will backpropagate, you will also have a derivative here. Let me go into the details. Let's define a target value. Let's assume that going left is better than going right at this point in time. So we initialize the network randomly. We forward propagate state 2 in the network, and the Q score for left is more than the Q score for right. So that's the action we will take at this point, is going left. Let's define our target, Y, as the reward you get when you go left, immediate, plus gamma times the maximum of all the Q values you get from the next step. So let me spend a little more time on that because it's a little complicated. I'm in S. I move to S next using a move on the left. I get immediate reward R, and I also get a new state S prime, S next. I can forward propagate this state in the network and understand what is the maximum I can get from this state. Take the maximum value and plug it in here. So this is hopefully what the optimal Q should follow. It's a proxy to a good label. It means we know that the Bellman equation tells us the best Q satisfies this equation. But in fact, this equation is not true yet because the true equation we have Q star here, not Q. Q star, which is the optimal Q. What we hope is that if we use this proxy as our label and we learn the difference between where we are now and this proxy, we can then update the proxy, get closer to the optimality, train again, update the proxy, get closer to optimality, train again, and so on. Our only hope is that this will converge. So does it make sense how this is different from deep learning? The labels are moving. They're not static labels. We define a label to be a best guess of what would be the best Q function we have. Then we compute the loss of where the Q function is right now compared to this. We backpropagate so that the Q function gets closer to our best guess. Then, now that we have a better Q function, we can have a better guess. So we make a better guess. And we fix this guess. And now we compute the difference between this Q function that we have and our best guess. We backpropagate up. We get to our best guess. We can update our best guess again. And we hope that doing that iteratively will end with a convergence and a Q function that will be very close to satisfy the Bellman equation, the optimal Bellman equation. Does it make sense? This is the most complicated part of Q-learning. Yeah.
So you're saying we generate the output of the network and then we compare it to the Q function.
We generate the output of the network. We get a Q function. We compare it to the best Q function that we think it is.
What is the best Q function that we
The one that satisfies the Bellman equation.
But we never actually computed the full Bellman equation.
We don't, but we guess it based on the Q we have.
Okay.
So basically, when you have Q, you can compute this Bellman equation, and it will give you some values. These values are probably closer to where you want to get to from where you are now. Where you are now is farther from this optimality. And you want to reduce this gap. To close the gap, you backpropagate. Yes?
Is there a possibility that these labels even diverge?
So the question is there a possibility for this to diverge? So this is a broader discussion that would take a full lecture to prove. So I put a paper here from Francisco Melo, which proves the convergence of this algorithm. So it converges. And in fact, it converges because we're using a lot of tips and tricks that we will see later. But if you want to see the math behind it, and it's a full lecture of proof, I invite you to look at this simple proof for convergence of the Bellman equation. Okay? Okay, so this is the case where left score is higher than right score. And we have two terms in our target, immediate reward for taking action left, and also discounted maximum future reward when you are in state S next. Okay? The tricky part is that, let's say we compute that. We can do it. We have everything. We have everything to compute our target. We have R, which is defined by the human at the beginning. And we can also get this number because we know that if we take action left, we can then get S next. And we forward propagate S next in the network. We take the maximum output, and it's this. So we have everything in this equation. The problem now is if I plug this and my Q score in my loss function, and I ask you to backpropagate. Backpropagation is what? W equals W minus alpha times the derivative of the loss function with respect to W, the parameters of the network. Which term will have a non-zero value? Obviously, the second term, Q of S go to the left, will have a non-zero value because it depends on the parameters of the network, W. But Y will also have a non-zero value because you have Q here. So how do you handle that? You actually get a feedback loop in this backpropagation that makes the network unstable. What we do is that we consider this fixed. We will consider this Q fixed. The Q that is our target is going to be fixed for many iterations. Let's say a million or 100,000 iterations until we get close to there and our gradient is small. Then we will update it and we will fix it. So we actually have two networks in parallel, one that is fixed and one that is not fixed. Okay, and the second case is similar. If the Q score to go on the right was more than the Q score to go on the left, we would define our target as immediate reward of going to the right plus gamma times the maximum Q score we get if we're in the state that in the next state and take the best action. Does this make sense? It's the most complicated part of Q-learning. This is the hard part to understand. So immediate reward to go to the right and discounted maximum future reward when you're in state S next going to the right. So this is hold fixed for backprop. So no derivative. If we do that, then no problem. Y is just a number. We come back to our original supervised learning setting. Y is a number, and we compute the loss, and we backpropagate. No difference. Okay? So compute DL over DW and update W using stochastic gradient descent methods. RMS prop, Adam, whatever you guys want. So let's go over this full DQN, Deep Q Network implementation. And this slide is a pseudocode to help you understand how this entire algorithm works. We will actually plug in many methods in this pseudocode. So please focus right now, and if you understand this, you understand the entire rest of the lecture. We initialize our Q network parameters, just as we initialize a network in deep learning. We loop over episodes. So let's define an episode to be one game, like going from start to end, to a terminal state. This is one episode. We can also define episodes sometimes to be many states. Like Breakout, which is the game with the paddle, usually is 20 points. The first player to get 20 points finishes the game. So episode will be 20 points. Once you're looping over episode, start from an initial state S. In our case, it's only one initial state, which is state 2, and loop over time steps. For propagate S, state 2 in the Q network, execute action A, which has the maximum Q score, observe an immediate reward R and the next state S prime, compute target Y, and to compute Y, we know that we need to take S prime for propagate it in the network again, and then compute the loss function, update the parameters with gradient descent. Does this loop make sense? It's very close to what we do in general. The only difference would be this part. Like we compute target Y using a double forward propagation. So we forward propagate 2 times in each loop. Do you guys have any questions on this pseudocode? Okay. So we will now see a concrete application of a deep Q network. So this was the theoretical part. Now we're going to the practical part, which is going to be more fun. So let's look at this game. It's called Breakout. The goal when you play Breakout is to destroy all the bricks without having the ball pass the line on the bottom. So we have a paddle, and our decisions can be idle, stay where you are, move the paddle to the right, or move the paddle to the left. Right? And this demo, and you have the credits on the bottom of the slide, shows that after training Breakout using Q-learning, they get a super intelligent agent which figures out a trick to finish the game very quickly. So actually, even like good players didn't know this trick. Professional players know this trick. But in Breakout, you can actually try to dig a tunnel to get on the other side of the bricks, and then you will destroy all the bricks super quickly from top to bottom instead of bottom up. What's super interesting is that the network figured out this on its own without human supervision. And this is the kind of thing we want. Remember, if we were to use input the Go board and output professional players, we will not figure out that type of stuff most of the time. So my question is, what's the input of the Q network in this setting? Our goal is to destroy all the bricks, so play Breakout. What should be the input? Try something. Yeah.
Ball position of the board at the bottom, position of bricks.
Position of the paddle, position of the bricks. What else? Ball position. Okay, yeah, I agree. So this is what we would call a feature representation. It means when you're in an environment, you can extract some features, right? And these are examples of features. Give me the position of the ball is one feature. Give me the position of the bricks, another feature. Give me the position of the paddle, another feature, which are good features for this game. But if you want to get the entire information, you'd better do something else. Yeah. The pixels. You don't want any human supervision. You don't want to put features. You just, okay, take the pixels. Play the game, you can control the paddle, take the pixel. So yeah, this is a good input to the Q network. What's the output? I said it earlier. Probably the output of the network will be 3 Q values, representing the action going left, going right, and staying idle in a specific state. That is the input of the network. So given a pixel image, we want to predict Q scores for the 3 possible actions. Now, what's the issue with that? Do you think that would work or no? Can someone think of something going wrong here? Looking at the inputs. Okay, I'm going to help you. If I give you, yeah, you want to try?
It's hard to know whether the ball is going up or down.
Oh yeah, good point. Based on this image, you cannot know if the ball is going up or down. So actually it's super hard because the action you take highly depends on if the ball is going up or down, right? If the ball is going down, and even if the ball is going down, you don't even know which direction it's going down. So there's a problem here, definitely. There's not enough information to make a decision on the action to take. And if it's hard for us, it's going to be hard for the network. So what's a hack to prevent that? It's to take successive frames. So instead of one frame, we can take 4 frames, successive frames. And here, the same setting as we had before, but we see that the ball is going up. We see which direction is going up, and we know what action we should take because we know the slope of the ball and also if it's going up or down. That make sense? Okay, so this is called a preprocessing. Given a state, compute a function phi of s that gives you the history of this state, which is the sequence of 4 last frames. What other preprocessing can we do? And this is something I want you to be quick, like we learned it together in deep learning. Input preprocessing. Remember the second lecture where the question was, what resolution should we use? Remember? You have a cat recognition, what resolution would you want to use? Here's the same thing. If we can reduce the size of the input, let's do it. If we don't need all that information, let's do it. For example, do you think the colors are important? Very minor. I don't think they're important. So maybe we can grayscale everything. That removes that converts 3 channels into 1 channel, which is amazing in terms of computation. What else? I think we can crop a lot of this. Like maybe there's a line here we don't need to make any decision. We don't need the scores, maybe. So actually, there are some games where the score is important for decision making. An example is football, or soccer. When you're winning 1-0, you'd better, if you're playing against a strong team, defend, get back and defend to keep this 1-0. So the score is actually important in the decision making process. And in fact, there are famous coach in football which have this technique called park the bus, where you just put all your team in front of the goal once you have scored a goal. So this is an example. So here, there's no park the bus, but we can definitely get rid of the score, which removes some pixels and reduces the number of computations. And we can reduce to grayscale. One important thing to be careful about when you reduce to grayscale is that grayscale is a dimensionality reduction technique. It means you lose information. But if you have 3 channels and you reduce everything in 1 channel, sometimes you would have different color pixels which will end up with the same grayscale value, depending on the grayscale that you use. And it's been seen that you lose some information sometimes. So let's say the ball and some bricks have the same grayscale value, then you would not differentiate them. Or let's say the paddle and the background have the same grayscale value, then you would not differentiate them. So you have to be careful of that type of stuff. And there's other methods that do grayscale in other ways, like luminance. So we have our phi of s, which is this input to the Q network. And the deep Q network architecture is going to be a convolutional neural network because we're working with images. So we forward propagate that. This is the architecture from Min, Kavuksoğlu, Silver et al. From DeepMind. Conv-ReLU, 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 2 fully connected layers, and you get your Q scores. And we get back to our training loop. So what do we need to change in our training loop here is we said that 1 frame is not enough, so we pre-process all the frames. So the initial state is converted to phi of s. The forward propagated state is phi of s, and so on. So everywhere we had s or s prime, we convert to phi of s or phi of s prime, which gives us the history. Now, there are a lot more techniques that we can plug in here, and we will see 3 more. One is keeping track of the terminal state. In this loop, we should keep track of the terminal state because we said if we reach a terminal state, we want to end the loop, break the loop. Another reason is because the y function, so Basically, we have to create a Boolean to detect the terminal state before looping through the time steps. And inside the loop, we want to check if the new S prime we're going to is a terminal state. If it's a terminal state, then I can stop this loop and go back, play another episode. So start at another starting state and continue my game. Now, this Y target that we compute is different if we're in a terminal state or not. Because if we're in a terminal state, there is no reason to have a discounted long-term reward. There's nothing behind that terminal state. So if we're in terminal state, we just set it to the immediate reward and we break. If we're not in a terminal state, then we would add this discounted future reward. Any questions on that? Yep. Another issue that we're seeing this, and which makes this reinforcement learning setting super different from the classic supervised learning setting, is that we only train on what we explore. It means I'm starting in a state S. I forward propagate this phi of S in my network. I get my vector of Q values. I select the best Q value, the largest. I get a new state because I can move now from state S to S prime. So I have a transition from S, take action A, get S prime. Or phi of S, take action A, get phi of S prime. Now this is what I will use to train my network. I can forward propagate phi of S prime again in the network and get my Y target, compare my Y to my Q, and then back propagate. The issue is I may never explore this state transition again. Maybe I will never get there anymore. It's super different from what we do in supervised learning, where you have a data set and your data set can be used many times. With batch gradient descent or with any gradient descent algorithm, one epoch, you see all the data points. So if you do 2 epochs, you see every data point 2 times. If you do 10 epochs, you see every data point 10 times. So it means that every data point can be used several times to train your algorithm in classic deep learning that we've seen together. In this case, it doesn't seem possible because we only train when we explore, and we might never get back there. Especially because the training will be influenced by where we go. So maybe there's some places where we will never go because while we train and while we learn, it will kind of direct our decision process, and we will never train on some parts of the game. So this is why we have other techniques to keep this training stable. One is called experience replay. So as I said, here's what we are currently doing. We have phi of S, forward propagate, get A. From taking action A, we observe an immediate reward R and a new state phi of S prime. Then from phi of S prime, we can take a new action A prime, observe a new reward R prime, and the new state phi of S prime prime, and so on. And each of these is called a state transition and can be used to train. This is one experience, leads to one iteration of gradient descent. E1, E2, E3, experience 1, experience 2, experience 3. And the training will be train on experience 1, then train on experience 2, then train on experience 3. What we're doing with experience replay is the following. We will observe experience 1 because we start in a state, we take an action, we see another state and a reward, and this is called experience 1. We will create a replay memory. You can think of it as a data structure in computer science, and you will place this experience 1 tuple in this replay memory. Then from there, we will experience 2. We will put experience 2 in the replay memory. Same with experience 3, put it in the replay memory, and so on. Now, during training, what we will do is we will first train on experience 1 because it's the only experience we have so far. Next step, instead of training on E2, we will train on a sample from E1 and E2. It means we will take one out of the replay memory and use this one for training. But we will still continue to experiment something else. And we'll sample from there. And at every step, the replay memory will become bigger and bigger. And while we train, we will not necessarily train on the step we explore. We will train on a sample, which is the replay memory, plus the new state we explore. Why is it good? Is because E1, as you see, can be useful many times in the training. And maybe E1 was a critical state. Like it was a very important data point to learn our Q function. And so on and so on. Does the replay memory make sense? So several advantages. One is data efficiency. We can use data many times. Don't have to use one data point only one time. Another very important advantage of experience replay is that if you don't use experience replay, you have a lot of correlation between the successive data points. So let's say the ball is on the bottom right here, and the ball is going to the top left. For the next 10 data points, the ball is always going to go to the top left. And it means the action you can take is always the same. It actually doesn't matter a lot because the ball is going up. But most likely you want to follow where the ball is going. So the action will be to go towards the ball for 10 actions in a row. And then the ball will bounce on the wall and on the top and go back down here, down to the bottom left, to the bottom right. What will happen if your paddle is here is that for 10 steps in a row, you will send your paddle on the right. Remember what we said when we asked the question, if you had to train a cat versus dog classifier with batches of images of cats, batches of images of dog, train first on the cats, then trains on the dogs, then trains on the cats, then trains on the dogs. We will not converge because your network will be super biased towards predicting cat after seeing 10 images of cat, super biased with predicting dogs when it sees 10 images of dog. That's what's happening here. So you want to decorrelate all these experiences. You want to be able to take one experience, take another one that has nothing to do with it, and so on. This is what experience replay does. And the third one is that you're basically trading computation and memory against exploration. Exploration is super costly. The state space might be super big. But you know you have enough computation, probably. You can have a lot of computation, and you have memory space. Let's use an experience replay. OK? So let's add experience replay to our code here. The transition resulting from this part is added to the experience, to the replay memory D, and will not necessarily be used in the iteration space. So what's happening is we forward propagate phi of s. We observe a reward and an action, and this action leads to a state phi of s prime. This is an experience. Instead of training on this experience, I'm just going to take it, put it in the replay memory. Add experience to replay memory. And what I will train on is not this experience, is a sample random mini batch of transition from the replay memory. So you see, we're exploring, but we're not training on what we explore. We're training on the replay memory. But the replay memory is dynamic. It changes. And update using the sample transitions. So the sample transition from the replay memory will be used to do the update. That's the hack. Now, another hack the last hack we want to talk about is exploration versus exploitation. So as a human, let's say you're commuting to Stanford every day, and you know the road you're commuting at. You know it. You always take the same road, and you're biased towards taking this road. Why? Because the first time you took it, it went well, and the more you take it, the more you learn about it. Not that it's good to know the tricks of how to drive fast, but like, you know the tricks, you know that this light is going to be green at that moment, and so on. So you build a very good expertise in this road, super expert. But maybe there's another road that you don't want to try that is better. You just don't try it because you're focused on that road. You're doing exploitation. You exploit what you already know. Exploration would be, OK, let's do it. I'm going to try another road today. I might get late to the course, but maybe I will have a good discovery, and I will like this road, and I will take it later on. There's a trade-off between these two, because the RL algorithm is going to figure out some strategies that are super good, and will try to do local search in these to get better and better. But you might have another minimum that is better than this one, and you don't explore it. Using the algorithm we currently have, there is no trade-off between exploitation and exploration. We are almost doing only exploitation. So how to incentivize this exploration? You guys have an idea? So right now, when we're in a state S, we're forward propagating the state, preprocessed state in the network, and we take the action that is the best action, always. So we're exploiting. We're exploiting what we already know. We take the best action. Instead of taking this best action, what can we do? Yep.
Monte Carlo sampling?
Monte Carlo sampling. Good point. Another one. You wanted to try something else?
Could have a parameter that's the ratio of times you take the best action versus exploring another action.
Okay, take a hyperparameter that tells you when you can explore, when you can exploit. Is that what you mean? Yeah, that's a good point. So I think that's a solution. You can take a hyperparameter that is a probability telling you with this probability, explore. Otherwise, with 1 minus this probability, exploit. That's what we're going to do. So let's look why exploration versus exploitation doesn't work. We're in initial state 1, S1. And we have 3 options. Either we go using action A1 to S2 and we get reward of 0. Or we go to use action 2, get to S3 and get reward of 1. Or use action 3 and go to S4 and get a reward of 1,000. So this is obviously where we want to go. We want to go to S4 because it has the maximum reward and we don't need to do much computation in our head. It's simple, there's no discount, it's direct. Just after initializing the Q networks, you get the following Q values. 4 propagate S1 in the Q network and get 0.5 for taking action 1, 0.4 for taking action 2, 0.3 for taking action 3. So this is obviously not good, but our network, it was randomly initialized. What it's telling us is that 0.5 is the maximum, so we should take action 1. So let's go. Take action 1, observe S2, you observe a reward of 0. Our target, because it's a terminal state, is only equal to the reward. There's no additional term. So we want our target to match our Q. Our target is 0, so Q should match 0. So we train, and we get the Q that should be 0. Does that make sense? Now, we do another round of iteration. We're in S1. We get back to the beginning of the episode. We see that our Q function tells us that action 2 is the best because 0.4 is the maximum value. It means go to S3. I go to S3. I observe reward of 1. What does it mean? It's a terminal state. So my target is 1. Y equals 1. I want the Q to match my Y, so my Q should be 1. Now I continue. Third step. Up. Q function says go to A2. I go to A2. Nothing happens. I already matched the reward. Fourth step, go to A2. You see what happens? We will never go there. We will never get there because we're not exploring. So instead of doing that, what we're saying is that 5% of the time, take a random action to explore. And 95% of the time, follow your exploitation. Okay? So that's where we add it. With probability epsilon, the hyperparameter, take random action A. Otherwise, do what we were doing before. Exploit. Does that make sense? Okay, cool. So now we plugged in all these tricks in our pseudocode, and this is our new pseudocode. So we have to initialize the replay memory, which we didn't have to do earlier. In blue, you can find the replay memory added lines. In orange, you can find the added lines for checking the terminal state. And in purple, you can find the added lines related to epsilon greedy exploration versus exploitation. And finally, in bold, the pre-processing. Any questions on that? So that's we wanted to see a variant of how deep learning can be used in a setting that is not necessarily classic supervised learning setting. And you see that the main advantage of deep learning in this case is it's a good function approximator. The convolutional neural network can extract a lot of information from the pixels that we were not able to get with other networks. Okay, so let's see what we have here. We have our super Atari bot that's going to dig a tunnel and is going to destroy all the bricks super quickly. It's cool to see that after building it. So this is work from DeepMind's team, and you can find this video on YouTube. Okay. Another thing I wanted to say quickly is what's the difference between with and without human knowledge. You will see a lot of papers mentioning that this algorithm was trained with human learned knowledge. or this algorithm was trained without any human in the loop. Why is human knowledge very important? Like, think about it. Just playing one game as a human and teaching that to the algorithm will help the algorithm a lot. When the algorithm sees this game, what it sees, it's pixels. What we see when we see that game, we see that there is a key here. We know the key is usually a good thing. So we have a lot of context, right, as a human. We know I'm probably going to go for the key. I'm not going to go for this thing, no? Same, ladder. What is a ladder? We directly identify that the ladder is something we can go up and down. We identify that this rope is probably something I can use to jump from one side to the other. So as a human, there's a lot more background information that we have even without knowing it, without realizing it. So there's a huge difference between algorithms trained with human in the loop and without human in the loop. This game is actually Montezuma Revenge. The DQN algorithm, when the paper came out in Nature, the second version of the paper, they showed that they beat human on 49 games that are the same type of games as Breakout. But this one was the hardest one. So they couldn't beat human on this one. And the reason was because there's a lot of information. And also, the game is very long. So in order, it's called Montezuma Revenge. And I think Ramtin Keramati is going to talk about it a little later. But in order to win this game, you have to go through a lot of different stages. And it's super long. So it's super hard for the algorithm to explore all the state space. Okay, so that said, I will show you a few more games that the DeepMind team has solved. Pong is one, Sequest is another one, and Space Invaders that you might know, which is probably the most famous of the three. Actually, no. Okay, so that said, I'm going to hand in the microphone to, we're lucky to have an RL expert. So Ramtin Keramati is a fourth-year PhD student in RL, working with Professor Brunskill at Stanford. And he will tell us a little bit about his experience, and he will show us some advanced applications of deep learning and RL and how these plug in together.
Thank you. Thanks, Kian, for the introduction. Okay, can everyone hear me now? All right, good. Cool. Okay, first, I have like 8-9 minutes. I have more? Okay, great. Okay, first question. After seeing that lecture so far, like how many are you thinking that RL is actually cool? Like honestly. That's like, oh, that's a lot. Okay, that's a lot. Okay, my hope is after showing you some other advanced topics here, then the percentage can even increase. So let's see. It's almost impossible to talk about like advancement in RL like recently without mentioning AlphaGo. I think someone right now wrote that on the table that it's almost 10 to the power of 170 different configuration of the board, and that's roughly more than, I mean, that's more than the estimated number of atoms in the universe. So one traditional RL algorithm, like before like deep learning and stuff like that, was like tree search in RL, which is basically go exhaustively search all the other possible action that you can take and then take the best one. In that situation, in AlphaGo, that's almost impossible. So what they do, that's also a paper from DeepMind, is that they train a neural network for that. They kind of merge the tree search with deep neural network that they have. They have two kinds of networks. One is called the value network, and value network is basically consuming this image, an image of a board, and telling you what's the probability that if you can win in this situation. So if the value is higher, then the probability of winning is higher. How does it help you? It helps you in the case that if you want to search for the action, you don't have to go until the end of the game, because the end of the game is a lot of steps, and it's almost impossible to go to the end of the game in all the simulations. So that just helps you to understand what's the value of each game like beforehand, like after like 40th step or 50th step, if you're going to win that game or if you're going to lose that game. There's another network of like policy network, which helps you to take action. But I think the most interesting thing of the AlphaGo is that it's trained from scratch. So it trains from nothing. And they have a trick called self-play, that there is two AI playing with each other. The best one replicate the best the best one and I keep it fixed, and I have another one that is trying to compete the previous version of itself. And after it completes the previous version of itself like reliably many times, then I replace this again for the previous one. And then I just turn. So this is a training curve of like a self-play of the AlphaGo, as you see. And it takes a lot of compute, so that's kind of crazy. But finally, they beat the human. OK, another type of algorithm, this is like the whole different class of algorithm called like policy gradients.
We have developed an algorithm called trust region policy optimization.
Oh, can I stop the...
This method was able to learn locomotion controllers for simulated robots from
scratch. Can you mute the sound, please? OK, great. So policy gradient algorithm. OK, what I can do is that I stop this from here. No, it doesn't work. OK, so here, like in the DQN that you've seen, you came and like, compute the Q value of each state. And then what you've done is that you take the argmax of this with respect to action, and then you choose the action that you want to choose, right? But what care at the end of the day is the action, which is the mapping from a state to action, which we call it like a policy, right? So what you care at the end of the day is actually the policy, like what action should I take? It's not really the Q value itself, right? So this class of methods that called like policy gradients is trying to directly optimize for the policy. So rather than updating the Q function, I compute a gradient of my policy, and I update my policy network again and again and again. So let's see these videos. So this is like this guy that is trying to reach the pink ball over there, and sometimes like gets hit by some external forces. And this is called like one of the algorithms called like PPO, which is a policy gradient, and try to reach to that ball. So I think that you've heard of OpenAI like 5, like the bot that is playing Dota. So this is like completely like PPO algorithm. And they have like a lot of compute showing that, and I guess I have the numbers here. They use like 180 years of play in one day. This is how much compute they have. So that's funny. There is another even funnier video. It's called competitive self-play. Again, the same idea with policy gradient. Is that you put two agents in front of each other, and they try to beat each other. And if they beat each other, they get a reward. The most interesting part is that, for example, in that game, the purpose is just to pull the other one out, right? But they understand some emerging behavior, which is, for us, human makes sense, but for them to learn out of nothing is kind of cool. So there's like one risk here that when they're playing, okay, this guy is trying to kick the ball inside. One risk here is to overfit. That's also cool. Okay, one technical point before we move. One technical point here is that here, wait, where is that? No, the next one. Okay, here that two agents are playing with each other, and we are just updating the person with the best other agent like previously. We are doing like a self-play. Is that you overfit to the actual agent that you're in front of you. So the agent in front of you is powerful, but you might overfit to this. And if I put the agent that is not that powerful, but is using a simple trick that the powerful agent like never uses, then you might just lose the game, right? So one trick here to make it more stable is that rather than playing against only one agent, you alternate between different versions of the agent itself, so it all like learns all the skill together. It doesn't overfit to the stuff. So there is another thing called like meta-learning. Meta-learning is a whole different algorithms again, and the purpose is that a lot of tasks are like similar to each other, right? Like for example, walking to left and walking to right and like walking in front direction, they are like same task essentially. So the point is, rather than training on a single task, which is like go left or go right, You train a distribution of tasks that are similar to each other. And then the idea is that for each specific task, I should learn with like a very few gradient steps. So very few updates should be enough for me. So if I learn, okay, play this video, is like at the beginning, this agent that has been trained with meta learning before doesn't know how to move. But just look at the number of gradient steps. Like after 2 or 3 gradient steps, it totally knows how to move. That's normally takes a lot of steps to train. But that's only because of the meta learning approach that we've used here. Meta learning is also cool. I mean, the algorithm is from Berkeley, Chelsea Finn, which is now also coming to Stanford. It's called model agnostic meta learning. So, all right, another point, this very interesting game, Montezuma Revenge, that Kian talked. How much time do you have? Okay, so you've seen exploration, exploitation dilemma, right? So it's bad if you don't explore. You're gonna fail many times. So if you do the exploration with the scheme that you just saw, like we call epsilon greedy, this is the map of the Montezuma game. And you're going to see only 2 rooms of that game if you do like exploration randomly. And the game, I think, has like 21 or 20-something different rooms that is hard to reach. So there's this recent paper, I think, from Google Brain, from Mark Billemer and team. It's called Unifying the Count-Based Methods for Exploration. Exploration is essentially a very hard challenge, mostly in the situation that the reward is sparse. For example, in this game, the first reward that you get is when you reach the key, right? And from top to here, it's almost like 200 steps. And getting the number of actions after 200 steps exactly right by like random exploration is almost impossible. So you're never going to do that. What a very interesting trick here is that you kind of keep a count on how many times you visited a state. And then if you visit a state that has like fewer counts, then you give a reward to the agent. So we call it the intrinsic reward. So it's kind of makes the...
Continue.
Okay, keep that. So it changes the looking for the reward in starting environment is also intensive. Like it has the incentive to just go and search around because we wanna increase the counts of the state that it has never seen before. So this gets the agent to actually explore a lot more. So it just goes down, visit like different rooms and stuff like that. So this game is interesting. If you search, there's a lot of people that recently are claiming to solve the game. And it's a huge research on like who can get the highest reward of this game. And it's just fun also to see the agent play. Any question on that? Any questions? No, all right. There is also another interesting point that would be just fun to know about. It's called imitation learning. Imitation learning is the case that, well, I mean, RL agent, so sometimes you don't know the reward. Like, for example, in Atari games, the reward is like very well defined, right? If I get the key, I get the reward. That's just obvious. But sometimes like defining the reward is hard. For example, when the car, like the blue one, wanna drive in some highway, like what is the definition of the reward, right? So we don't have a clear definition of that. But on the other hand, we have a person, like we have human experts that can drive for us. And then we see, oh, this is the right way of driving, right? So in this situation, we have something called imitation learning that we try to mimic the behavior of an expert. So not exactly copying this, because if we copy this and then you show us a completely different state, then we don't know what to do. But from now we learn. And this is like one example. And there is a paper that called Generative Adversarial Imitation Learning, which was like from Stefano's group here at Stanford. And that was also interesting. Well, I think that's advanced topic. If you have any questions, I'm here, Kian. Question? No?
Okay, so I guess for next week, so there's no assignment. You guys have finished C5 and you know about sequence models now. We want you to spend a lot of time on this project. The project is a big part of CS230, as you know. And there's going to be project TA mentorships, and this Friday we will have TA sections with reading research papers. We will go over the object detection YOLO and YOLO V2 papers from Redmond et al. Okay, see you guys. Thank you.